Hello everybody and welcome to our video on inverse trigonometric functions. So now we're going to really be hearkening back to a previous topic that we spent some time on, which is that of inverse functions. So we dealt with that in its origin in a video a long time ago, and then we talked a lot more about inverse functions when we talked about the logarithm. So now we're going to talk about inverse functions of the trigonometric functions. And this becomes a bit more complicated than our previous cases. So recall that in order to have an inverse, a function must be one-to-one. And also that the two equivalent definitions of an inverse function are that f of f inverse of x equals x and f inverse of x equals x, meaning that when I compose inverse functions, I get my input back. And the second definition being y equals f of x if and only if x equals f inverse of y, meaning that inverse functions switch inputs and outputs. So that's all fine and well, but we have a little bit of a problem because this condition is part of the definition. Function must be one-to-one, meaning that there should only be one input for each output. And when we look at the graph, for example, of sine of x here, this does not pass the horizontal line test, meaning that there are multiple inputs corresponding to the same output. So this function would not have an inverse. So how are we going to deal with that, right? So why do we want the trig functions to have inverses? It's the same reason we want any function to have an inverse, because it helps us to give us a tool to solve equations. It also helps us solve other types of real-world problems, like, for example, I can tell, based on information from earlier in this trigonometric material, if I know the angle that a car has rotated through, that a wheel has rotated through, I know how much distance the car has traveled, right? My input is the angle, my output is the distance, right? What if I want to invert that relationship, right? Well, that becomes very challenging when you're dealing with trigonometric functions. What if I want to know, okay, well, this is my output for my trig function. What angle was corresponded to that output, right? What angle gave me that output? Well, there's infinitely many angles that can give you any output, so it becomes an impossible question to answer. So what we're going to do is actually kind of create some new functions, and we're going to call these, for the purpose of this class, restricted trigonometric functions. So let's take a look here. I'm looking at my graph for sine of x, and I'm thinking, man, what could I do to this graph so that it's actually a one-to-one function? Well, imagine that I just took this graph and I cut it at negative pi over 2 and pi over 2. And we just erased everything else. And if we're only looking at this graph that we've restricted between negative pi over 2 and pi over 2, then we should ask ourselves, is this graph one-to-one? And surely it is. Each of these outputs, each of these y values along our blue graph, is only reached by one of the inputs between negative pi over 2 and pi over 2. And so what we can do is we can define a new function. We're going to define the restricted sine function. So the restricted sine function is the function y equals, and I'll put sine sub r of x, which is equal to sine of x under the condition that the domain is restricted to being between negative pi over 2 and pi over 2, and the range is, of course, still the same, right? We're still hitting every output. So just to elaborate on this point a little bit before we go much further, I chose this restriction for a good reason, because if I tried to pick the restriction between 0 and pi, this would not have been a one-to-one function, right? I still would have not passed the horizontal line test. Now, there are other places that would have worked, like pi over 2 to 3 pi over 2 is technically a valid place to restrict this sine function, but we restricted it to negative pi over 2 and pi over 2 because that centers it at 0, and most of us know our values for trig functions at 0 better than we do values further down the line. So it just makes things a little easier if we consider our restrictions around 0. So the important thing that comes out of this restricted sine function is that this function is now one-to-one. And if the function is one-to-one, then we can define an inverse function, right? So that leads us to our definition for sine inverse. Sine inverse means that y equals sine inverse of x means that x equals sine of y, where y is between negative pi over 2 and pi over 2, and x is between negative 1 and 1. So notice what we've done here is that we're defining our inverse trig function in the usual way, that we're switching the inputs and outputs of our original trig function, but we're doing it with just the restricted version of the trig function. So this restricted version has domain negative pi over 2 to pi over 2 and range negative 1 to 1. So sine inverse has range negative pi over 2 to pi over 2 and domain negative 1 to 1. And that's really the whole key. The whole key to defining these inverse trig functions is just that we have to come up with reasonable restrictions on the original trig functions. So with that in mind, how do we think about these trig inverse functions? We usually think of this like this. So if I say y equals sine inverse of x, sort of think of this like, what angle y between negative pi over 2 and pi over 2 gives x as the value for sine of that angle. So in other words, it's just asking the opposite question, right? Whereas the sine function says, my input is an angle, what y value do I get in the unit circle? The inverse trig function says, here's a y value, what angle would have given you that? But with the extra condition that I only want you to look at angles between negative pi over 2 and pi over 2. Otherwise, you would have infinitely many answers. If I asked you, sine inverse of the square root of 2 over 2. That's like saying, what angle gives you the square root of 2 over 2? Well, technically, there's infinitely many answers there. There's pi over 4, and there's 3 pi over 4, and then there's 9 pi over 4, and so forth and so on. So here, by restricting in this way, there will only be one answer to the question. So again, here's just that restatement. And now with that in mind, let's look at our graphs. So this restricted sine function from negative pi over 2 to pi over 2. The blue graph is our restricted sine function. So I should really say sine r of x here. And then if I flip this graph over the y equals x line, I switch my inputs and output values. That gives me this graph here, y equals sine inverse of x. So our x value will go from negative 1 to 1 now, and the y will go from negative pi over 2 to pi over 2. Okay, so now let's move on and talk about cosine. So we have a similar problem here, But if you try to do your restriction from negative pi over 2 to pi over 2, it won't pass the horizontal line test. So we can't use the same restriction for cosine that we used for sine. So instead, we're going to restrict cosine to 0 to pi. So again, we still get all of the output values from 1 all the way down to -1. We get every output value for cosine, but now we're only looking at the inputs from 0 to pi, and this makes this function 1 to 1 now. So when we look at the restricted cosine function here, we're just looking at cosine with domain from 0 to pi, including 0 and pi, and range is still -1 to 1. So that leads us to the definition for cosine inverse, that y equals cosine inverse of x means that x equals cosine of y, where y is between 0 and pi, and x is between -1 and 1. So again, what did we do? We just switched the domain and range. So now my range is 0 to pi for the inverse function, and my domain is -1 to 1. So one of the things I want to emphasize real quick is that because of the nature of defining these restricted functions and how we need to look at the graphs to determine where we can make these 1 to 1, really understanding these trig function restrictions and remembering them boils down to how well you know these graphs. So it's really important that you practice drawing the graphs of sine and cosine, that you can graph them quickly, and then that looking at those graphs, you can determine where the natural place would be to restrict these functions. All right, so now we'll take a look at the Cartesian graph for cosine inverse, and we have a similar thing going on here. Here's our restricted cosine graph, right? It's from 0 to pi, looks like this. And if we draw the y equals x line here in red, if we flip this graph over this y equals x line, well, the mirror image that we get over that line is going to look like this, y equals cosine inverse of x. Okay, and we'll take a look at one more graph here for tangent. And we want to figure out how to restrict the graph of tangent. And this one I think is the most obvious choice of all, because we look at this one, it repeats every pi, and it's very clear that we just need to break this from negative pi over 2 to pi over 2, because that has one full repeat of tangent in it. So we make the same restriction. Restricted tangent is from negative pi over 2 to pi over 2. So the domain is negative pi over 2 to pi over 2. And the range is still negative infinity to infinity. So now, that allows us to define tangent inverse as y equals tangent inverse of x, means that x equals tangent inverse of y, where y is between negative pi over 2 and x is between negative infinity and infinity. All right, so when we look at the graphs for tangent, the graph for tangent from negative pi over 2 to pi over 2, this is a restricted tangent. If I flip this over the y equals x line, my graph looks like this. And one thing you'll notice is that we had x asymptotes at negative pi over 2 and pi over 2, vertical asymptotes, right? And we have horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2 for tangent inverse. That should make sense. Again, these are inverse functions. They switch inputs and outputs, and likewise, they switch asymptotes. All right, so we're not going to go through and draw the pictures of all of these, but I do encourage you to try that on your own. Draw your graph for cotangent of x, draw your graph for cosecant and secant of x, and see where these restrictions are, and make sure that you understand why those restrictions make sense. So cotangent inverse of x means that cotangent of y equals x, where x is between negative infinity and infinity, and y is between 0 and pi. So the angle restriction for cotangent is 0 and pi. Y equals cosecant inverse of x means that cosecant of y equals x, where the absolute value of x is greater than or equal to 1, and y is between negative pi over 2 and pi over 2, but excluding 0. And the reason we have to exclude 0 is because cosecant is undefined at 0. Y equals secant inverse of x means secant of y equals x, where the absolute value of x is greater than or equal to 1, and y is between 0 and pi. And in this case, y cannot be pi over 2. And again, that's because secant of pi over 2 is undefined. Now, with all of our inverse functions defined and our conditions out of the way, we'll look at just one other notation real quick. So oftentimes, various textbooks will use arc notation interchangeably. So it means the same thing. Sine inverse of x means arcsine of x. They're the same thing. Cosine inverse of x means arc cosine of x. And some authors feel that the arc notation is less likely to be confused with reciprocals. But it's my view that as long as you give a proper treatment of inverse functions and make sure that students understand that inverse functions are defined on that operation of composition and that they are not the same thing as reciprocals, as long as you give that a thorough treatment, I don't think there's any additional confusion or clarity added by using arc notation. But just understand that when you see these two things, they're the same thing. Tangent inverse of x and arc tangent of x, it's the same thing. Cotangent inverse of x and arc cotangent of x. It's the same thing. There's no difference. Okay, so just a summary of some of the key properties here to keep in mind. So remember that inverse functions, when you compose them, f of f inverse of x is x, and f inverse of f of x is x. Right, that's our definition for inverse functions. And what do we see here? Well, sine of sine inverse of x equals x. But we have to think about the restrictions here. This is really the key with dealing with the trig inverse functions, is that because we had to artificially restrict them, the definition for inverse functions is restricted likewise. So here, the sine inverse can only input between negative 1 and 1, right? So this thing can only output between negative 1 and 1. And when we look at sine inverse of sine of x equals x, sine inverse can only output between negative pi over 2 and pi over 2. That's the restriction for the output of sine inverse. So if x is something that doesn't fall in this interval, then we have to figure out a different solution here. So again, all of these restrictions are just the restrictions that we looked at when we looked at the graphs of these things. We're thinking about this as the output of the composition of these functions. So I'm looking at the output of sine inverse, the output of cosine, the output of cosine inverse, so forth and so on. Okay, so with that out of the way, let's go ahead and take a look at a proper example here. Evaluate y equals cosine inverse of 0. So y equals cosine of inverse of 0 means cosine of y equals 0 under the condition that y is between 0 and pi. And that's the key thing that will cause students to make mistakes, is they don't think about the condition here. So whenever you rewrite this, you take the inverse problem and rewrite it in terms of the original function. You have to think about, okay, what's the restriction on my angle here? And I know that y has to be between 0 and pi, so I ask myself, what angle y gives me 0 for cosine between 0 and pi? Oh, that's pi over 2. So y equals pi over 2. And then for example 2 here, we do the same process, right? Evaluate y equals arcsine of pi of 1/2. Now, hopefully at this point you do have your trigonometric function values down well enough that you can do what I just did, which is say what angle gives me 0 for cosine and just spit that angle out. But let's say that you have a tough time with that still. That's okay. You can just reverse the process that we learned for drawing our angles, right? So if I say cosine of y equals 0, I have to think to myself, what point on the unit circle gives me 0 for the x value? Oh, it's this point. So if this is the point that gives me 0 for cosine, now what's my angle? Oh, it's pi over 2, right? So you can just kind of reverse the process. Instead of drawing the angle first and then the point, you can draw the point first and then figure out the angle from it, just reversing that same process you've done before. Okay, so evaluate y equals arcsine of 1/2. So again, we say, well, that's the same thing as saying sine of y equals 1/2. But we have to think about the condition on sine. And for the restricted sine function, we only allow angles y between negative pi over 2 and pi over 2. In other words, the output for arcsine can only be between negative pi over 2 and pi over 2. So let's say I don't know off the top of my head which angle this is. We can draw this. I have to be in either the fourth or first quadrant, negative pi over 2 to pi over 2. And when I look at my sine value, sine of y is 1/2, which means the y value of my triangle has to be 1/2. And so if I reverse my thought process, I know what angle is across from 1/2. Pi over 6 is always across from 1/2. So that tells me that y equals pi over 6. Okay, so now let's take a look at y equals cosine of cosine inverse of 2/3. So the key here is the restriction we have to be worried about with all of these composition problems is the output. So when I look at y equals cosine, I have to think about what outputs do I get for cosine, not cosine inverse. What outputs do I get for cosine? And cosine can output anything between -1 and 1. And I look at cosine of cosine inverse of 2/3, and I just ask myself, is 2/3 between -1 and 1? It is, so this is just 2/3, right? This is f inverse of f of x equals x slash f of f inverse of x equals x, right? When I compose inverse functions, I always get back x. And so when I look here at example 4, I have to do the same thought process. I have to say, okay, what outputs do I allow for sine inverse? And for sine inverse, the outputs are negative pi over 2 to pi over 2. And I ask myself, is pi over 6 in that interval? Yes, it is. So sine inverse of sine of pi over 6 is just pi over 6. Done. It's that easy. So this is a perfect example of why if we really understand what inverse functions are, then a lot of our problems involving them can be pretty simple. But now here's one that gets a little more complicated. So evaluate y equals cosine inverse of cosine of 5 pi over 4. So I have to think about what outputs can cosine inverse have? Well, cosine inverse has to output between 0 and pi. And I have to ask myself, is 5 pi over 4 in this interval from 0 to pi? No. So I can't output 5 pi over 4. That can't be the answer because cosine inverse can't spit out that number. Cosine inverse can only spit out numbers between 0 and pi. So, well, what do we do then? Well, it's simple enough. We just evaluate what's inside the function, plug it in. So cosine of 5 pi over 4. Remember, 5 pi over 4 is pi plus pi over 4. So we draw pi and another fourth of pi. And so that means my little reference angle here is pi over 4. And so my sine value here would be negative root 2 over 2, and my cosine value would also be negative root 2 over 2. So cosine inverse of cosine of 5 pi over 4 is equal to cosine inverse of negative root 2 over 2. So now we can think of this problem in our other way, as y equals cosine inverse of negative root 2 over 2, which implies cosine of y equals negative root 2 over 2 under the condition that y is between 0 and pi. Okay, so let's recap so far. We're not done yet. So we evaluated cosine of 5 pi over 4. I just drew my angle 5 pi over 4, found the cosine value. And I said, okay, plug that in. I get negative root 2 over 2. So now cosine of y should be equal to negative root 2 over 2, where y is between 0 and pi. Okay, so I'm going to do my reverse process. Now I'm looking for the angle and I have the side, but I'm between 0 and pi. So I go, what angle between 0 and pi gives me negative root 2 over 2 for cosine? Well, if cosine is negative, I have to be in the second quadrant. So this is negative root 2 over 2. But if this is negative root 2 over 2, then my other side is positive root 2 over 2. And across from that side, root 2 over 2, I always have to get the angle pi over 4. But pi over 4 isn't the angle I want. I want the angle from the positive x-axis. That's 3 pi over 4. So that's my angle, 3 pi over 4. So one of the things that I want to illustrate here is if we take a look at these two graphs, what do we see? That they have the same reference angle. The angle that corresponded to 5 pi over 4, the reference angle is pi over 4. We get the same reference angle for this case. And in fact, this triangle is just the similar triangle that's directly above this one. In other words, you're basically looking for the same reference triangle that's just in the quadrant that fits inside your restriction for your angle, in this case from 0 to pi. Hopefully that makes some sense. All right, so now we want to evaluate cosine of pi over 6 plus cosine inverse of negative root 3 over 2. But this is really just an angle, right? The output for cosine inverse is an angle. Inputs for cosine are angles, so outputs for cosine inverse are angles. So we think of this as theta equals cosine inverse of negative root 3 over 2, which is the same thing as saying cosine of theta equals negative root 3 over 2 under the condition that theta is strictly, or is inclusively between 0 and pi. So I'm going to repeat my same old process. Again, maybe you've got these down really well, and that would be ideal. It'd be great if you've got it down to the point where you can say, oh, cosine of theta is negative root 3 over 2, so theta must be blah. Right? If you can just spit that out instantly, that's perfect. But if not, that's okay, because you can always just draw your picture. So our angle has to be between 0 and pi, so somewhere up here, and we should get a negative value for cosine. So that tells me we're in the second quadrant. I'm either in the first or second, so I must be in the second quadrant. And if cosine is negative root 3 over 2, my triangle should look like this. This is negative root 3 over 2. And if this side is negative root 3 over 2, my other side is 1/2. My triangle is a little sloppy there. Let me just make that a little bit better. And across from 1/2 is always pi over 6. But of course, pi over 6 isn't the angle I want. I want the angle from the positive x-axis. So that makes this 5 pi over 6. So theta equals 5 pi over 6. So this was kind of side work for this problem, because the actual question was to evaluate cosine of pi over 6 plus this. So this becomes cosine of pi over 6 plus 5 pi over 6. Pi over 6 plus 5 pi over 6 is pi. So this becomes cosine of pi. And cosine of pi is -1. If you need to, you can draw that angle and check that. All right, so that's it for that example. So now we're going to look at how we can use sketches to evaluate these compositions of trig and trig inverse functions. So again, it's a lot of the same kind of ideas. We're just solving slightly different problems here. So here we've got y equals sine of cosine inverse of 3/4. And what I should think about is I'm really asking what's sine of some angle theta. All right, that's really what I want to know. So what is sine of theta? But theta is cosine inverse of 3/4, which means that cosine of theta is 3/4, where theta is between 0 and pi. So I can draw this, and I can draw a triangle from it because I know, hey, 3/4 is my adjacent over my hypotenuse, right? If we think back to that SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, or we can think of cosine of theta as just being the x divided by the r. That's fine too. So we've got 3/4 here, and cosine is positive. So since I'm between 0 and pi, but cosine is positive, that means that my angle has to be in the first quadrant. And here my r value is 4, and my x value is 3. And what I need to figure out is what y is, because I want to find sine of this angle, right? This is theta. I want sine of theta. So I apply the Pythagorean theorem. 3 squared plus y squared equals 4 squared. That's 9 plus y squared equals 16. Subtract the 9, you get y squared equals 7. So y equals the square root of 7. So finally, that leads me to the value for sine of theta. Sine of theta is y over r, so that's just the square root of 7 divided by 4. So again, it is really important that when we're looking at problems like this, that we're considering that we're thinking about the outputs of our inverse trig functions as being angles, right? That's the key thing. The input of a regular trig function is an angle, which means the output of an inverse trig function is an angle. So when we look at these, we always say to ourselves, oh, this is actually just an angle. Now, how do I figure out the information from that angle? Well, I don't need to know what the angle itself is if I know what the triangle that's formed out of that angle looks like. That's all I really need to know. Okay, so example number 8 here, use a sketch to evaluate y equals sine of tangent inverse of 13/5. So more of the same idea here. We think of this as really being sine of theta, and theta here is tangent inverse of 13/5. So that means tangent of theta is 13/5 under the condition that theta is between negative pi over 2 and pi over 2. All right, so we got to go back to our conditions for the inverse tangent. It can only output between negative pi over 2 and pi over 2. So now when we go to draw this thing, we're in either the first or fourth quadrant, but the value of tangent is positive here. So that tells me I must be up in the first quadrant. And remember that tangent is y divided by x. So this is 13 and this is 5. And that means that what I need to find is my hypotenuse r. So 5 squared plus 13 squared equals r squared. That's 25 plus, let's see, I think 13 squared is 169. Let me double check that before I put something that's wrong. Yeah, that's 169. So 169 plus 25, that's going to be 194. So r here is equal to the square root of 194. Now I could see if I can simplify that. I'm not going to actually bother at this time. You might need to simplify this further if you're working on homework, something like that. But it's not super important for our purposes here. So we've got r equals the square root of 194. So what I want is sine of theta. But I know that sine of theta is y divided by r. So that's 13 over root 194. Now what I will do though is rationalize. I'll just multiply by root 194 over root 194. That gives me 13 root 194 divided by 194. Okay, so that's it for that example. Let's go ahead and move on to this one. Use a sketch to evaluate y equals tangent of sine inverse of -3/4. So again, we think of this like tangent of theta, where theta is my input here, sine inverse of -3/4. And that's equivalent to saying sine of theta equals -3/4. Of course, with the condition that theta is between -pi/2 and pi/2. So now I want to draw it, figure out what my triangle looks like. So -pi/2 to pi/2, that's somewhere in here. But this time sine of theta is negative, so I need to draw this triangle in the fourth quadrant here. And remember that sine is my y divided by r. So my y is -3, and my r is 4 here, and this is my x. So in order to figure out what tangent of theta is, I need to know what x is. So, okay, well, that's the same old, right? It's -3 squared plus x squared equals 4 squared. 9 plus x squared equals 16. Subtract the 9, I get 7. So x equals the square root of 7. And I know that it's positive root 7 because it's on the right-hand side. So now when I go to evaluate tangent of theta is just y divided by x. That's -3 divided by root 7. And I will go ahead and rationalize that. All right. So now we're kind of done with the main examples here. We're just going to look at a couple facts that may come up. You may see these. These aren't things that we use a ton with trigonometric inverse functions, but I just want to make sure that they're there so that you have them for reference in case you see them. So the first thing is that you do have odd symmetry with sine inverse. So sine inverse of -x equals -sine of x. And you can actually see that in the graph of sine inverse. Looks like it's rotated 180 degrees. In other words, the reflection over the y-axis and the reflection over the x-axis are the same thing, right? And cosine inverse does not give you odd symmetry or even symmetry, but it does give you some other kind of odd property here that, again, rarely, but sometimes comes up. Cosine inverse of -x equals pi minus cosine inverse of x. So let's take a look here real quick. So we're just going to look at these transformations. So cosine inverse of negative x, that looks like this. We just start with our y equals cosine inverse of x graph, and we just flip it over the y-axis. So this is cosine inverse of negative x. And if we look at the negative cosine inverse of x, I take this graph and I make it negative. That flips it down. And then if I add pi, it shifts it up. So the point here is that this graph for cosine inverse of negative x is the same as the graph we get for pi minus cosine inverse of x. So you may see these properties. They do rarely get used, but they're not going to come up a lot. So don't worry too much about these. All right, that's it for our video on inverse trigonometric functions. Thank you for watching.